Let's add a little bit more to this idea of climate sensitivity, especially in terms of how the models are doing, because we rely on models not only for weather prediction and climate prediction, which we haven't talked about much, but you cannot talk about future climate change without using the models, because we rely completely on models to project what could happen in the future if the human activities continued this way, or if human beings started to worry about climate change and try to control their impact on climate. Okay, so we can start with the idea of delayed warming again. I don't mind repeating these points many times so that you are aware, plus those who are watching for the first time or just picking this podcast can still follow some of the ideas. Vostok ice core again showing slow cooling, glaciation, rapid warming. So we are in the warming phase, so we have to worry about the feedbacks that can happen very fast in the warming phase, right? We said ice albedo feedback goes really fast. When you start melting glaciers, albedo decreases, more energy is absorbed, more warming happens, and glaciers melt faster and faster, and we have very rapid warming. We looked at the Younger Dryas as a recent example. And we are saying, compared to the past changes where the orbital forcing initiated the warming in temperature, which leads, and then the changes in glaciers happen, either glacier buildup or glacier melt, and then CO2 response. And the slow glaciation is related to cooling, drier atmosphere, reduced snowfall rates. Right now, we are, since Industrial Revolution, increasing carbon dioxide, so this is already old. We are out of the range of CO2 seen in the last million years or more, and methane is of course sky high as well. Remembering this is parts per billion and this is parts per million by volume. Delayed warming basically means that the feedback seen here in terms of the relation between the change in temperature versus change in CO2 hasn't started yet, because the system is in a transient response in the sense of the climate sensitivity that we talked about. Remember, when we are ramping up CO2, climate begins to respond, but it's in a transient state because it's still adjusting to the increased CO2, increased energy trapping of the outgoing long wave, going into glacier melting, evaporation, ocean uptake, and so on. So eventually, if this is the real feedback in the system, then we would get continued warming, even if we capped off CO2 at some level at present. Okay, that's the point. In the models, as we said already, detection comes mostly from observations where you look at a change. It could be temperature, it could be changes in the type of rain, for example, extreme rainfall, or increased droughts, or just complete disappearance of some species, early arrival of birds, increased length of the growing season, early arrival of spring. Could be any signal that you observe, and then you say, okay, that's a robust change signal. Then you have to do attribution to say what caused it, right? That's the whole business of detection and attribution. So there are volcanic forcings involved, solar forcing involved, carbon dioxide involved, and so on. And here is the observed warming signal, for example, which is always a poster child for global warming. We already saw that. We can run a model and show that models are able to produce the 20th century warming reasonably well. There are many details here. So these yellow envelope here is simulation by multiple models, and each model can do multiple realizations of the 20th century based on various things that we haven't gone into. The other detail to remember is that given the anthropogenic greenhouse gas increases and the volcanic forcing, radiation, solar activity changes and everything, models can produce the trend, the warming, the overall energy budget, but they don't necessarily produce the internal variability or natural variability from year to year when you integrate for so long. There are reasons for it. When you do weather prediction, it has to produce temperatures, precipitation, humidity, winds, etc. for the next few days, and you have to actually compare with observations to make sure that the forecast was accurate or not, right? And with climate prediction, you predict out to a season, to multiple seasons. For example, El Nino, you might say in April or May that this year will be an El Nino, so by December, January, February, you get to test whether that's really an El Nino. But when you integrate so long, the difference is that the weather forecasts and climate forecasts are initialized in the beginning before the integration begins with all the data that's observed for ocean temperatures, ocean thermocline depth, heat content, humidity, winds, everything, and then you integrate the model forward. Okay, but in this case, it's not really initialized. It is given the CO2 level, let's say at the beginning of the Industrial Revolution at 280 ppm, and it's integrated by increasing just CO2, giving it volcanic eruption knowledge and changes in solar activity. So you cannot expect year-to-year variability to be captured. For example, we said 97-98 in the real world was a very strong El Nino, but in the model 97-98 need not be a very strong El Nino, for example, seen here. But the volcanic eruption can be seen in these dips. Okay, that's something to remember. Nonetheless, we use the models. We give it all the quantities that affect the radiative forcing or the radiation balance at the top of the atmosphere, like volcanic forcing because it blocks sunlight, solar activity because it changes the amount of energy coming in, and you also include several details like land use change, for example, deforestation, and then you make another simulation after you convince yourself that the model is doing the trends properly. You take out all the anthropogenic forcing. So you take out the CO2 increase, related land use change, and so on. And you show that the temperatures don't warm up when you do that. And that allows you to conclude that the warming is totally related to human activities, especially in terms of land use change and greenhouse gas emissions. That's the main story. So let's look at some of the problems that we have to deal with. Models are never perfect. Okay, given the top of the atmosphere radiation from the sun, they can produce everything. They produce El Ninos, monsoons, ITCZ, winds, mid-latitude eddies, energy transport, equator to pole temperature gradient, Antarctic circumpolar current, and so on and so forth. The models may or may not have a land ice model to build glaciers, but now the models have that. They may or may not have sea ice models, depending on how far back you go, but now they have sea ice models. Their thermohaline circulation will not be as will not compare to the observations very well, but the observations are not perfect either because thermohaline circulation is not easy to observe, as we said. So you have to deal with all these kind of issues. Nonetheless, you can compare things like that. So the relative frequency of warming in degrees centigrade per decade for the period of just 1998 to 2012, where we said there was a global warming pause. So observations say the warming rate was very low at about 0.1 degrees per decade or less. When you compare a previous period of 1984 to 1998, before the so-called global warming pause, observations said the warming was order 0.3 degrees centigrade per decade. And if you take a longer period, 1951 to 2012, then the warming is somewhere around 0.1 degrees centigrade per decade. So if you look at various models and the frequency with which, the relative frequency with which they produce the observed warming, because you make multiple simulations by changing various things just to see the sensitivity of the warming, for example, to urbanization, to agriculture, to irrigation, to deforestation, and so on. And you get a range of values, and you can see that most models actually did not do this slowdown of global warming pause. Okay, they just missed it. None of them predicted beforehand that there could be a pause coming. Okay, if you look at 1994 to 1998, again, the models deviate from the observed warming quite a bit, unfortunately. But if you look at the longer period, then the models are right close to where the observations are. So it just confirms that on the long anthropogenic time scales, the response to so-called external forcing, human beings are taking out fossil fuels from under the earth and burning it and changing the radiative balance. So we are producing an external forcing similar to changes in solar activity, or similar to volcanoes which take out stuff from below the earth and throw it into the atmosphere. So the response to external forcing on longer time scale is reasonable. So that gives us hope that if you look for warming or cooling in the 21st century, maybe models are reliable. So this is just an assumption we have to go with eyes wide shut, knowing what the biases in the models are, and being aware of how to interpret the model outputs. Okay, that's very critical. There are very good papers written on this by people like Tim Palmer and Bjorn Stevens and so on that you can read up to understand how to take care of model biases, especially at regional and local scales. Global mean warming can be done well. Does that mean that the warming in your backyard can be done well? Not really. So you have to be careful about that as well. And there is a very nice paper by Palmer and Stevens on that, just I think from 1 or 2 years ago.